Okay, welcome everyone to the last session. Samuel will tell us more about vertex algebra and curves in the moduli space of sheaves.
Thank you. So I'm going to briefly recap from last time. What we did and sort of what the general goals of this program are. So we constructed a Lie algebra. G T star E, which is spanned by elements W gamma A B and a central element. A and B run over the integers. Gamma runs over a basis 1, sigma 2 point for the cohomology of an elliptic curve with a bracket W.
Listen, you can make one of the C's, which is not complex number, like really bold thing. Like the fill the handle there.
So which one do you? Oh, okay.
Standard notation for C and then something else. This other.
Something like that.
Yeah, something like that.
Okay. Yeah, I don't want it to be like a regular C because, yeah, here we have gamma 2. And I'm going to index the elements by this. This is the determinant of A, B, C, D, W, A plus C, B plus D, gamma 1, convolution gamma 2. Plus delta A plus C0, delta B plus D0, B, pairing of gamma 1 and gamma 2, and then blackboard, not blackboard, but bold-faced C. So we got this Lie algebra, and then G T star E acts cyclically. On a space that I'm going to call V A phi 1 phi 2. Which is a positive vertex algebra of this hyperbolic lattice. Tensor the Fock module for the odd cohomology of the elliptic curve. Where phi 1 and phi 2 act as multiplication by the 0 modes where A and B are both equal to 0. So A is the action of W 0 point. Phi 1 is the action of W 0 sigma 1. Rather, phi I is the action of multiplication by these. Yeah, the hope is to extend this to a Hopf algebra whose category of modules is generated by these modules V, and get some sort of algebra which we can call like U H bar upside down T1 upside down T2 of G T star E that acts via a evaluation into, sorry, this should be some sort of loops that acts via evaluation to V.
L is loops, you said?
Yeah, maps from a curve into the Lie algebra.
Is this hope will be realized during the talk, or will be somehow still outstanding?
Basically, still outstanding. I mean, there'll be some definition as just generated by the operators that I'm going to describe together with multiplication by tautological classes on moduli spaces. But in terms of saying anything else about this, Lie algebra describing it as like a quantum group is not going to be realized.
But it will still be a Vertex quantity.
That I don't know. So this is the analog of like the Yangian, and I don't actually know if the Yangian itself is a vertex algebra.
No, like the image in this representation.
The image in this representation should be generated exactly by this GT star E. So it generated by this Lie algebra, which acts as Fourier coefficients of vertex operators. The higher modes, yeah, precisely as it's defined. The other modes are also going to be represented as a completion of a vertex algebra. Because the way I'm going to define this is going to be like generated by like Fourier modes of vertex operators here in this representation. But in tensor products of representation, I'm going to say basically nothing.
But in the that would be like what Hilbert scheme of points.
Just in the Hilbert scheme of points, yeah. This is just the rank 1 module.
And then the idea would be that high rank would be somehow that structure.
Right, higher rank would be captured by a Hopf algebra structure on this algebra. Similar to the types of things we talked about at the beginning of the talk yesterday. Right, and so what I want to say is that this.
Sam, I apologize. The higher rank sheaves on that surface, are they like fundamentally different, or they're just birational to some sort of scheme of points?
Fundamentally different, yeah. The tensor product of two modules is infinite dimensional. There are versions of higher rank sheaves on this surface that are birational, and those are just these same the image of these modules under SL2 automorphisms. The tensor product is something truly fundamentally different. In particular, doesn't have finite dimensional weight spaces. So yeah, I'll also say something about some other modules that'll sort of become clear that are essentially the exact same thing as this. But I'm not going to say anything about the Hopf algebra structure. Great. So how are we going to construct this? And yeah, so the idea is that this is going to be the cohomology of moduli space of framed sheaves. So this should be union over all B. So these are sheaves on E times P1 framed at divisor at infinity. So here I'm going to assume that F is simple. So in particular, it's a coherent sheaf on an elliptic curve, and so it's also stable. And you can use SL2 to send it to a line bundle, and then tensor by a line bundle to send it to the trivial line bundle. Sort of crucially is that what I didn't say were what are these odd variables phi1 and phi2 is we're actually going to.
I apologize, but this is so to speak. Yeah, this module by itself is not SL2 invariant.
No, it's not SL2 invariant. Yeah,
so it's one of those. Right?
Yeah, it's one of these. So this should be V, and this is the class of the framing sheaf, which we assume to be simple. We can construct the modules for all simple framing sheaves and then say something about their tensor products.
So can you remind me what is the mu?
That's a V. Yeah, so MVF is, I'm going to write its set of closed points is the set of E phi such that E is a torsion-free coherent sheaf on E times P1. And phi is a fixed choice of isomorphism from E restricted to the divisor at infinity to f. So strictly speaking, this is going to be the evaluation, the specialization of this module where these odd variables are 0. So this is this where phi1 is equal to phi2 is equal to 0. And then if we want to specialize these to different values, we have to take this relative to a moduli space of simple sheaves on the elliptic curve. So let J RD GCD of RD is equal to 1 be a moduli.
It's like the variable that kind of scales that automorphism.
Precisely, A just scales the automorphism. And we're going to let JRD be a moduli space of sheaves of rank R in degree D on the divisor at infinity. And then we're going to take relative moduli spaces over the cohomology. So we're going to take, so let curly F universal over J RD be the universal simple module here. And then we replace the equivariant cohomology of MVF.
It's pretty unfortunate that phi is the automorphism possible.
The var phi and phi here.
Yeah. One can rename that phi. Psi.
I'm going to use psi a ton later, so let's call this like lowercase f for framing. Right, so this is the specialization at phi1 is equal to phi2 is equal to 0 of the cohomology of MVF universal, where the base ring of this cohomology is JRD.
What's that subscript on coherent sheaves?
Torsion free. Yeah, so these stacks of frame torsion free sheaves are representable in the case of E cross P1, and our framing is a simple sheaf. And so these quasi-projective varieties are actually these a priori stacks are representable by quasi-projective varieties. One more time.
How does the sheaves there depend on B?
So they're torsion-free sheaves whose discrete data is Turing character is determined by V. And only some V are going to be compatible with this framing. So this has to be an isomorphism, which specifies its rank and its degree along the P1 factor.
So D infinity means what?
So P1 has coordinate Z, and it's just the elliptic curve over infinity in P1.
And the JRD or IRD, but it's the module space on this E times infinity.
Of E infinity, yeah, it's a moduli space of sheaves on an elliptic curve, and famous result of ITEA, which is that if the coprime of the rank in the degree of coprime, then this moduli space of like stable sheaves, semi-stable sheaves is actually just isomorphic to the elliptic curve itself. And so in particular, its cohomology is a free supercommutative ring generated by two odd variables, the A and B cycles on the Jacobian. And those are going to act as the evaluation parameters by which the zero modes of this algebra act as multiplication by. Right, and of course, I have a T here, but we can also just replace this with C star H bar and say we're taking this over the stack BGA. And so all of the zero modes act by just cohomology classes in our base, the base string of our moduli spaces. Okay, so how am I going to identify geometric action of this like algebra on these modules as cohomology spaces?
So just making sure, what is T?
Big T is the torus, yeah, so T is equal to C star H bar. H bar scales scales P1, in particular restricted to 0, it scales the cotangent fiber of the elliptic curve. And then we also have C star A, which just scales this framing F. So it acts on our moduli spaces. It actually really acts trivially in these cases on account of the fact that our framing is simple.
But
And
it acts non-trivial on the universal bundles.
right, yeah, it has a non-trivial weight on the universal bundles. That's right.
And to quotient by BGA, you mean BC star A?
Yeah, I'm mixing algebraic B, C star A. And so, yeah, the multiplication by the zero modes is just given by cohomology classes in the base string. Okay, so how are we going to geometrically describe this action?
Is there an abstract reason why we expect such actions to be able to be liftable to cohomology of some moduli space? I think this is what we're doing, right? Am I getting this wrong? So we're having some action and we're trying to interpret it as being actually acting on
Cohomologies of moduli spaces.
spaces.
Yeah, this is a sort of standard thing. It's
It's like, that's what people in geometric representation theory do.
yeah, that's the field of geometric representation theory, that we have some sort of action of a Lie algebra. Yeah. If he doesn't understand the reason, that there's nobody else who would. So
Yeah,
we just take it as a fact of life that these sort of things happen.
Okay, thanks for your help.
But you know, what's a matrix? You're interested. A matrix is like a correspondence between two finite sets. It's like a model of two finite sets. From finite sets to some space.
Good. Okay.
Okay, now I'm going to kind of switch gears in order to sort of construct operators that act according to this Lie algebra. And the background is going to seem to actually be quite different. So what we're going to do is we're going to talk about quantizations. Of the cotangent bundle of an elliptic curve, or the cotangent bundle of orbifold stacked curves, where C is a projective curve, gamma is a finite group. That acts faithfully on that curve. And these are going to be provided by the theory of non-commutative P1 bundles. So first we're going to define a category of sheaf bimodules. So let SH bimod. So I'm going to call this curve curly C. SH bimod curly C times curly C.
The stack.
This stack, yeah, is going to be represented by a curly version of the same curve. So sheaf bimodules is the same thing as sheaf bimodules, which are gamma times gamma equivariant on our curve times our curve, which is a full subcategory of the category of gamma times gamma equivariant coherent sheaves on the product of our two curves. And what is it? It's equal to the set of E in co gamma squared of C times C, so that E is finite over both curves CI. And given a sheaf bimodule as such, so given.
Sorry, I'm getting lost here. Why do we suddenly want to consider the division of this variable?
It's like in school geometry. You have to solve a problem and then you make some auxiliary construction first, and that's an auxiliary construction.
Yeah, we're trying to construct operators that realize these generators of this Lie algebra. And the way we're going to do this is by deforming our problem, deforming our moduli spaces, finding like generators on the deformed problem, which is considerably simpler, and then reduce to the undeformed problem, where then we can get the result that we want. So this is provides a deformation of the whole problem that's going to be related to roots of this corresponding Lie algebra. So the space of, long story short, what I'm going to tell you in the next little bit is that the space of quantizations of these curves is going to be the same as the Cartan subalgebra of the corresponding Lie algebra.
Is it quantization of T star E on or
Quantizations of T star E. So this is some sort of scheme, and we're going to replace it with some sort of non-commutative scheme.
But what does the word read?
Is it or
On. Oh, sorry. Or. That's or. This is or. Yeah, that's an R. So T star E, or a more generalization, is the cotangent bundle of these orbifold curves. And basically what we're doing is we're embedding non-commutative geometry into commutative algebraic geometry using the theory of sheaf bimodules. So what is going to be non-commutative multiplication is, well, they're going to act by some sort of matrix, and our matrices are going to act by convolution, now on sheaves instead of on cohomology classes. So how are these non-commutative elements of our ring going to act? Those are going to be sections of our sheaf bimodules. And so given E in SH bimod, and then also given some A, which is a coherent sheaf on C, let's say, call this C1 and C2 for the first and second factors. We're going to define A tensor C1 convolution by the sheaf bimodule. This symbol refers to pi2 push forward of pi1 pullback of A tensor our sheaf bimodule. And on account of the fact that we're in the equivariant setting, what I mean is the equivariant push forward. So we then are going to have to take like gamma invariants. It's finite out of both, and so it preserves the category of coherent sheaves exactly. So these push forwards, you don't have to take a derived push forward at all. Yeah, which is a very, very nice aspect of this theory. So let's assume. So we're going to call.
Then probably pi 2 lower than
Yeah. So call E locally free if pi 1 and pi 2 push forward of E are locally free. And then define its usual left and right adjoints via the adjunction isomorphism. So we need home. I get these right. I always get this incorrect. Hum C2 A tensor C1E to a coherent sheaf B has to be the same as hom on C1 of A to
the same as just flat over both local free or both factors.
if it's flat over both sides and maybe like locally free on its support. I'm not super sure.
It's just a curve.
The curve can be like non-reduced. It's very generally going to be like some sort of yeah. So that just use this definition. So yeah, the curve. In our case, the curve is going to be like a non-reduced curve, but over families, it's going to have like fibers where it's reduced. So the non-reducedness isn't going to be preserved under pullbacks. And so let's keep this this definition. Hom C1 A B tensor C2 of its right adjoint, then hom C2 A B tensor C1E is equal to hom C1 okay, so in this setup, Vandenberg has defined a notion of a non-commutative P1 bundle. Over a curve, and then the generalization to an orbifold curve is somewhat straightforward. So definition, a non-commutative P1 bundle is the following data that we get from this construction is one, a sheaf Z algebra which is a category enriched in sheaf bimodules whose objects are the integers. So we have AI, I plus 1. We have AJJ. We have various AIJs. So we have a collection for every like pair of integers, a particular sheaf bimodule. We also have a category of modules. So category of modules. And sitting inside of here are collections, mi, i's and z, with an action for every mi, and then this is going to be tensor over c I mod 2 aij, a map from here to mj. So we have a sheaf C algebras, a category of modules, and then we're going to define d dg over the projectivization of a particular rank 2, meaning rank 2 over either factor sheaf bimodule, to be graded modules for a particular Z algebra A, which I'm going to define in a second, modulo those that are bounded.
So can I say again, what's the first sheaf of the algebra? Is it that one?
So this is a category whose like objects are labeled by the integers and whose arrows we assign sheaf bimodules. Then we have our module category is just like modules over this category. So they also have pairs of integers, and then at each of these sites we get like a sheaf of a category. It's like a yeah. I'll explain this right now. So that the point is that we're trying to generalize the construction of like modules over P1 bundle over something by taking equivariant C star equivariant modules over non-commutative C2 without the origin. This is a fiber bundle over E dual without the origin over our curve. And so these have like parameters x and y that don't commute with each other. E dual is the dual of a particular sheaf bimodule E. And then how do we want to think of these modules? Well, we have mi at each of these sites. So we have like m1, m2, m3, and m4. And then a2 is given by sort of multiplication as a vector by our variables x and y. And then we also have some relations between the aij. So if A24 is actually just three-dimensional, so it's spanned by like all pairs of multiplication modulo a single relation, which is defined by the adjunction. So we have some sort of relation which is approximately, I don't know, xy is equal to qyx between multiplications by the coordinates on the C2. And the way we do this is we define like a category of modules over this like Z algebra, some sort of categorical algebra construction, and then we take the quotient by bounded modules. And this is the same as constructing like sheaves on a P1 bundle over some space by constructing them on C2 bundle without the origin. They're forced to be C star equivariant, and then you get rid of all of your torsion modules over the fibers.
drew on the right corner, right bottom corner is this is an example of such a module.
Yeah, so a module for this algebra, which is going to be like functions here, is at each integer a sheaf over your underlying curve. And then to specify the action of the multiplication of the coordinates on these C2, so homogeneous coordinates for our non-commutative P1, what we're going to do is we're going to specify matrix multiplication by those elements.
Okay.
Since we don't have access to like actual multiplication by elements, we have to embed it into commutative algebraic geometry by identifying them as convolutions of sheaves.
There's something non-commutative going on here, so as to say, or?
Yeah, precisely because the multiplication by the coordinates is given by convolution. This is not commutative. So this we can think of as taking M, and we're keeping track of multiplication by xy, and it gets sent to say like mx plus my, and it's generated by the convolution by our particularly sheaf by module E, and then we have relations coming from a junction. It's a general construct. Yeah, so it's a general construction of Vandenberg of non-commutative P1 bundles applied to the setting, which is in some sense slightly more general than Vandenberg's story because our curves are stacks. But it has a ton of applications. So the really cool applications of this theory is that D modules and like Q difference modules are basically on exactly the same footing. So it's no harder to do it this way with like differential operators or non-commutative like completions of adding a divisor at infinity to D modules to like adding a divisor at infinity to difference modules over the curve. So we have C2. So this E is a rank 2 sheaf, which we want to think of as C2. And we're multiplying by.
Is this E the same as the kernel E?
Yeah. This.
Why did we pick E? Something else? I'm not seeing the big picture here.
E is just going to be some choice of rank 2 bundle, rank 2 sheaf by module over our curve.
Anytime I want to quantize something, I want to rank 2 things.
On a curve, so the quantization, yeah. So now I'm going to tell you all of the quantizations that we care about. So I'm going to list all of our possible E's that you're going to care about, and it's going to give us like projective completions of twisted differential operators on our stacky curves.
So just do like a quiz about. I thought your E was leading the quantum space like a curve, the kernel of some operator E, like leading the.
Yeah, that's right.
C. But now you're saying E2 is leading over C. What does that mean?
It's a non-commutative version of this. So it's rank 2 on account of the fact that our sheaf on the product. Yeah, maybe I'm going to do all of the examples that we care about, and it's going to be nicer than this abstract setting. And it's going to be kind of clear that sections of this sheaf by module E are going to correspond to like multiplication by functions and also action of differential operators. So all of our examples. Here we have C. Here we have our same C, which we can think of as C1 and C2. And for us, we're gonna restrict entirely to not difference operators, but differential operators. So this is going to correspond to the fact that our sheaf bimodule is going to be supported on second order formal neighborhood of the origin. So E is supported on the fat diagonal. And for us, we're also going to have an exact sequences where embedded into E, we have the structure sheaf for the diagonal. We have some sort of E, And then here we're going to have the diagonal push forward of the tangent bundle. So this is going to give us, so the non-commutative P1 bundle associated to this. So dg projectivizations of this E is the same thing as the derived category of like the projectivization of D modules on our curve direct sum the structure sheaf of the curve. So that if we want to take multiplication by dz on our curve, we're going to convolve by a section of the pulled back of the tangent bundle after choosing some sort of splitting. And then here, if we have some sort of coordinate on our curve, it's going to come from convolution. Different extensions correspond to twistings of the differential operators, including infinite twists, which give us commutative surfaces. So yeah, so what we're doing is we want to take functions or sections of sheaves on our curve. We want to multiply them by local sections of the structure sheaf, and we also want to take derivatives of them. And the way we're going to do this is we're going to take a section of some sheaf, pull back to the double tensor product, and then which section we're going to take in this extension is going to tell us whether we're going to multiply by a function or take a derivative. And then this framework gives us a DG category that looks like a P1 bundle, which is D modules on our curve together with the divisor at infinity.
So what do you mean when you say D sub C, or in projective on that D sub C?
So this is actually should be sort of dual. So this doesn't literally make sense in mathematics because we can't take like a non-commutative like sheaf of modules, which is a non-commutative ring, and take its projectivization. So instead, what we're going to do is we're going to use this like categorical Z algebra structure in order to provide a replacement of this, where we have homogeneous coordinates on fibers such that their projectivization gives us, D modules together with a line at infinity. Right. So this doesn't make sense. This makes sense because I'm defining it this way.
So your rank 2 is because we're looking at second order neighborhood?
Yeah, rank 2 is a second order neighborhood, so it pushes forward to something of rank 2 here. And then the real reason is, yeah, we want like rank, the cotangent bundle of a curve is like a rank 1 bundle over the curve, and its projective completion is going to come from something of rank 2. So a key property is that this DG category also has an extremely nice description in terms of causal data. So this is DG equivalent to the DG category of causal data, depending on our sheaf bimodule. The DG category of causal data of E is the set of triples where we have A, B, and some map psi. A and B are coherent sheaves on our curve, and psi is a map from A tensor C1A to B. So this is, on account of this DG equivalence, this is like much more closely related to the actual D module map. So if you take this example, this is literally just the same as giving the structure of a D module on the curve. But the sort of cone of this map keeps track of also its restriction to infinity. So it keeps track of the boundary data, which is extremely important for us.
So still really confused. So where does that X and Y correspond to in that?
In this example, X is Z, and Y is derivative with respect to Z. It's differentiation with respect to that coordinate.
Why don't we
Because we're taking, this is like how you get like P1 out of C2.
For what?
We want, sitting inside of this, we want like a dense open set, which is actually just D modules on our curve. And so we're just adding a divisor at infinity to like the total space of D modules on our curve. And so we want like P1, we don't, I mean, I suppose you could also study like the total space of this, but it's not going to deform to something in like projective algebraic geometry. It's kind of like studying.
Is it some technical stuff or?
It's the whole purpose of this step was to construct like a quantization of a surface, E times P1.
Apply this to like T star C?
That's, yeah, this is exactly to T. So T star is quantized to differential operators.
Yeah, no, I know, but could we have done this had we not studied, had our starting point not been T star E, but just the familiar sheaves on an AN surface, or like, I mean, instance ones on an AN surface, or?
Yeah, so if you want to do AN, you're probably going to take our curve to be like A1 modulo Zn, and then its cotangent bundle is our AN surface. So we're quantizing one of the directions of that AN surface. We're doing it in a slightly different way than doing it on P2. It's like we're taking like P1 cross A1 rather than the completion, which is P2.
The outcome of that, all of that would be that some kind of modular and sheaf from these different surfaces with the deformation of our original Hilbert scheme.
Yeah, exactly. And at the level of Hilbert scheme, this is like a theorem in the non-orbifold curve. It's a theorem of Eric Rains, who's actually proved that the Hilbert schemes deform as flat projective families.
Right. Other than this stuff, what sort of with what sort of precision do we need to know about this?
The other important thing is duality. So dualities between these surfaces are going to give rise to duality properties of the quantum differential equation. So precisely, like while invariance of the quantum differential equation is going to rise exactly from like derived equivalences of these surfaces, and so it's so there's going to be a toroidal, an elliptic Weil group, an extension of an elliptic Weil group that acts on these quantizations, acts on the space of these quantizations, that gives rise to the Weil invariance of the quantum differential equation. And so that's why we kind of need to know about it precisely, because we need to, I don't know, understand these dualities and how they give rise to monodromy invariance or Weil invariance of the QDE. All right, so so now I'm going to say something exactly about these dualities. In this setup, we have various dualities. Let's take just those which are generated by convolution. By taking the tensor product with a line bundle on our curve. So
what kind of duality? You mean this causal duality or some Fourier duality?
It's going to be like a Fourier duality. So they're going to give us derived equivalences between these DG categories for different quantizations. So it's going to exchange different choices of quantizations of the cotangent bundle.
How does this causal duality work? Maybe you don't want to know.
It's
just conceptually why you're getting causal duality and anything else.
This is just a description of this, so that basically because the causal duality here is like the Beilinson transformation along the P1 direction. So like P1 is derived equivalent to a quiver, the quiver with 2 nodes and 2 arrows going between them. And we're just doing like a non-commutative and relative version of that, is this causal duality statement. Says that relative to our base curve, and after we take this non-commutative deformation, we can study this like complicated categorical algebra construction just using this this causal data on our corresponding curve. It's yeah, generalization of the Beilinson transfer, the Beilinson resolution on P1. Right, so it's we're going to take dualities which are generated by just taking tensor products with line bundle, autoequivalences of bounded derived category of our curve, and Verdi duality. I'm going to explain these two in a second, but Verdi duality is extremely, extremely natural in the description of causal duality. It just takes A, B, psi to the corresponding adjoint. So we have A, B, psi. It's mapped to B, A, psi adjoint. And it gives autoequivalences for different choices. The end result is that our space of quantizations of the cotangent bundle of C mod gamma is given by this cohomology group, which is the zeroth Hochschild homology of our stacky curve, defined to be extensions in C times C of the push forward of the diagonal by the structure sheaf. This admits the action of a reflection group, which I'm going to call the Weil group of a Kac-Moody group associated to our stacky curve.
What will be the curve?
I'll explain how to go from a stacky curve to a Weil group, and then say how this acts on quantizations.
But in our situation, what's C, what's gamma?
So we mostly care about the case where C is an elliptic curve and gamma is trivial. But in order to prove what I want to prove, we actually have to allow C to be an elliptic curve and gamma to be a finite group of automorphisms. But the theory is, at least this part of the theory, it doesn't really matter what the curve is.
You're saying you're not talking about the one value, about how
Yeah, a very large, like an infinite, an infinite Weil group, which is going to be the Weil group of something that looks like the affinization of a Kac-Moody algebra. So it's a very large Weil group of dualities that acts in the setup.
And it's generated by the distribution of things.
These are all dualities that act in this context, and they generate a reflection group on this zeroth Hochschild homology. And they act by derived equivalences of the corresponding quantizations. Great. So
Can you say something like, they give a like a deformation in the surface of a P1 bundle over some curve, right? And then in particular you'll have some deformation of the diagonal bimonture on that surface, and you push that forward to just the product of two bases, and that's your E.
So my E is
some kind of rank 2
on the product of two things, of two curves. That's right. Yeah, which is an extension of the diagonal, which is the just multiplication by functions, by the tangent bundle, which is dual to the symbol of a differential operator.
Suppose it's not differential operator. Suppose there's some kind of deformation. Then still be some kind of rank 2 thing over the.
Exactly. Yeah.
And is that rank 2 is supposed to somehow think of push forward or something called surface, which is like kind of some kind of deformation diagonal there? Is it not like that?
Probably.
Okay.
Yeah, there should also be like a way of relating these deformations of the cotangent model of curve to yeah, the like deformations of P1 cross E, like probably there's going to be like a, I don't know, a natural exact sequence you can get on Hochschild homology of the curve in P1, yeah, they give deformations of the surfaces, but we're going to do it in this framework in order to have access to all these dualities. Right, so what is HH0, which is going to be the same as the Cartan subalgebra, the Kac-Moody hat associated with this curve, where if our curve, let's take to either be an elliptic curve or a P1 with a parabolic structure at various points, it gives rise to a Dynkin diagram where we replace the base P1 with also points. This is a picture of our curve, yeah. C, yeah. So C is equal to this, and then our Dynkin diagram of our. It's just that we've taken like an the same thing is they're stacky points, and then I'm just telling you the stabilizer of the stacky points. As a symmetric group.
Well, what's the status? It runs through some finite group.
Yeah, finite group. Yeah.
That is.
That's going to be like Z mod 4Z.
Oh, okay.
So you're telling me some stacky curve, or what is it?
Yeah, this is a stacky curve or a curve with parabolic structure, and it's generically smooth, and then it has stabilizers at various points. And this gives rise to a star-shaped Dynkin diagram.
For all the local singularities, we look at the Dynkin diagrams.
You combine them all into a larger Dynkin diagram, where we're assuming that the curve is, we've taken a large enough group of automorphisms, so the curve is P1, and we've made that the sort of star shape at the center of our Dynkin diagram. And we're left with a star-shaped Dynkin diagram. Out of this, we're going to get a Kac-Moody algebra, and then we're going to take the algebra of loops into that Kac-Moody algebra, so the affine Lie algebra associated to Lie algebra with a symmetric invariant form. And then inside of here, we're going to take H KMC.
I suppose this is really like putting these Dynkin diagrams together. It's really a construction you came up with. Can you say a bit?
I don't know if I came up with that. That's a fairly standard structure, for example, in like the theories of class S that you know, or just in general in the world of parabolic Higgs bundles. That when you start with curves with parabolic structure, you can associate it to them these star-shaped Dynkin diagrams, where the base curve kind of plays the same role as you know, one of your like orbifold points, or the
Base curve has to be P1.
I'm going to say it's either P1 or it's for.
And then the Q is not the one you're going to get loops at that project.
I'm only describing like the Kac-Moody sector, which so I'm not for this, which doesn't affect the while group except for this Verdier duality part. It's probably going to be loops at that vertex. But let's only take this to either be P1 or an elliptic curve with no orbifold points. If it's in a elliptic curve with no orbifold points, we're going to get like the Kac-Moody part of our G T star E, and which is the toroidal GL0. And in these other cases, we're going to get loops into a Kac-Moody algebra.
Just to confirm, if it's an elliptic curve, you just get your Dynkin diagram, or how do you draw your Dynkin diagram?
I wouldn't draw a Dynkin diagram. It's like the Dynkin diagram of A-1, so it's an empty Dynkin diagram. So I put it on the board actually for the So yeah, so how do I want to think of this? Is we have some sort of large space, which is the zeroth Hochschild homology of our curve, which is also going to be the Cartan of this like Kac-Moody algebra. It has the sort of level 0 hyperplane is deformations corresponding to like commutative surfaces. So HH0 commutative is equal to like delta perp. It's a root hyperplane perpendicular to loops. We also have hyperplanes perpendicular to the real roots of our underlying Kac-Moody algebra. So these are alpha perp, where alpha is in the root system associated to the non-affine Kac-Moody algebra. And then you have duality images of all these hyperplanes. And the point is that on one of these hyperplanes, so on some sort of hyperplane associated to a root, there's a hyperplane HH0 alpha, which is equal to alpha perp, is a hyperplane where the total space of like D modules associated to E over our curve has coherent sheaves of class alpha. So for a generic point, so take a generic point. So generically, we can scale everything to like a level 1 hyperplane. So this is level 1. And the point on the level 1 hyperplane are in one-to-one correspondence with twisted D modules. So a point here under an isomorphism between this and the level 0 hyperplane, which is isomorphic to the Picard of our Stacky curve tensor the complex numbers. If we take a line bundle here, which is some complexified tensor product of the line bundle, at the level 1 hyperplane, the corresponding bimodule extension is the projectivization of twisted D modules, say of order less than or equal to 1. And if we take a generic twisting, so generic L, there are no D modules which are also coherent. So in particular, for a non-generic twisting, we know to get a D-module structure, the like monodromy has to be trivial. And so if we take any like rank 1 sheaf that isn't degree 0, we're not going to be able to get like D modules on those line bundles by the Riemann-Hilbert correspondence. And this is a generalization of that fact.
This alpha curve is hyperplane where it's taught as coherent sheaf class alpha.
The total space, this is sitting inside of our P1 bundle where we've gotten rid of the divisor at infinity. So we're saying, you know, in our P1, so we have our like, so this is our non-commutative, here's our curve. It's not actually a product, but we can think of it as having a P1 factor. Here's our commutative divisor at infinity. And then all of this stuff is non-commutative. Over outside of the hyperplane alpha, we're not going to be able to get coherent sheaves, which means something which is like
alpha is like abstracted from just some
it's the yeah. So that those are going to correspond to like Chern classes of coherent sheaves in our non-commutative P1 bundle. So alpha is equal to the Chern character of some sheaf A. A is in coherent sheaves of the projectivization of order less than 1 twisted differential operators in our curve. And in the like commutative world, yeah, and so this let's start with the hyperplane, which is delta perp. Delta perp is exactly those points where we have like points in our surface. So on the level 0 hyperplane, our surface is actually commutative, and so we have points in our surface. Whereas once we leave that level 0 hyperplane, there are no coherent sheaves that are like dimension 0 sheaves.
This is like a parameter space describing all possible quantization of some deformation of coherent sheaf on the original surface.
Yeah. And so torsion-free sheaves deform in a like flat way over this family, but torsion sheaves like only exist over root hyperplanes in the space. So the simplest one is this sort of commutative hyperplane where our non-commutative surface has points in it. But then there are all of these other hyperplanes. Yeah, at infinity everything's commutative. But yeah, so as a D module, that's why I said over the total space of differential operators. So if it's going to actually just be like coherent and live away from the divisor at infinity, this
why because if you think about what happens with
this it's this extension, right? So this is always just multiplication by functions. And so at infinity, we're taking the projectivization of differential operators of order less than 1. And so sitting inside of here, we just have multiplication by functions. And that's always like commutative multiplication, which is just, you know, we're at the divisor at infinity, and that's, you know, a sheaf at the divisor at infinity is just a sheaf on the curve. And so it remains just completely commutative.
But it's the absence of monogram. Is that the one and only instruction to let it equivalent? Like if I have a D module with 0 monogram, that's okay.
The better way I think to think of the abstraction is in the language of causal data, the cone of this map has to be 0. So the actual like D module multiplication map like needs of the restriction of D module multiplication map by the tangent bundle needs to be 0. So we need to be able to like have like differentiation needs to be surjective. So I think that's by Riemann-Hilbert might be equivalent to this monogamy constraint. I'm not super sure. Yeah, probably best to think about it as the cone of the restriction to one of these factors has to vanish, because that cone is precisely the restriction of the divisor at infinity, and that needs to be 0, right, whether there's such a thing exists.
That A tensor E to B is like the, like you said, like representation of the Billington Weaver of some sheaf tensors of rank 1 vector on the vector space, and like the second node, the wider cone of that set.
So the cone, so it's the restriction if we have a sheaf in here. So E restricted to the divisor infinity is the cone of, well, we have, a map from A tensor C1, and then we're going to take this like diagonal subsheaf that embeds into C1 of our sheaf bimodule, and then this goes to B. And the cone of this map is the restriction of the divisor at infinity. So when you can get modules of particular Chern characters, so A and B have to have the same Chern character because they're, you know, both the push forward onto C of this torsion sheaf. And in order for this to not hit the divisor at infinity, the restriction of the divisor at infinity has to be 0. And so it exactly corresponds to, yeah, the existence of these where A and B are the same, and then the map of this cone, the cone of this map has to be 0. Great. And then, yeah, and then the point is that this while group acts on the space of these quantizations.
The quantizations are parameterized by HH0, and the hyperplane itself is going to play which role in this?
They're root hyperplanes in the Cartan subalgebra of this Lie algebra.
So they will be play a special role in the action.
They're in particular the while group acts on roots, and so it exchanges one of these hyperplanes with another. And the real reflections are those which are actually reflection through those roots.
And I'm sorry if I missed any details here, but like the hyperplane itself, those quantizations lying on that hyperplane or parameterized points on that hyperplane, are they special somehow, or is it what?
Yeah, they're special in the sense that there exist coherent sheaves of a particular class on those quantizations.
On the quantizations themselves. Okay, I'll take that from you. Thanks.
Okay, so now I'm going to say, yeah, our sort of main examples are going to give us the elliptic while groups of types D4 and type E. So our main examples, so C is an elliptic curve, gamma is Z mod KZ, let's see, K is equal to 1, 2, 3, 4, 6. So I'll just draw a table of, here's the order of gamma, here's the dimension of HH0, here's a corresponding like Lie group, which is G Katsmoody of the curve, and then here's a while group. So the order is 1, 2, 3, 4, and 6. In this case, we have a 2-dimensional space because the chord of any smooth curve is just 1-dimensional. In order 2, we have a 6-dimensional space. Order 3, yeah, these are dimensions 8, 9, 10. The like Katsmoody group in this case is like affine GL0. In this case, it's affine D4, affine E6, affine E7, affine E8. And the while groups are the elliptic while groups associated to the corresponding elliptic root systems. So for any elliptic curve, we have the Kummer involution that just sends the point to its negative. And then for very special elliptic curves, we have additional automorphisms, namely rotation by 3 if it's a hexagonal lattice, that same Z mod 2Z, and then also, yeah, rotation by 4 if it's a square lattice, and then both involution and rotation by 3 on the hexagonal lattice. So it's this. Well, it's this together with those generated by Verdi duality.
So this GL0 hat is some kind of fiction.
A GL0 hat is just the affine Lie algebra associated to loops into GL0. So that is perfectly well defined. It's just it's zero dimensional. But in this case, the Kac-Moody part, in this example, the Kac-Moody is just extremely different from what should be the full Lie algebra. So the expectation is that G Kac-Moody hat associated to a curve C sits inside of larger Lie algebra associated to a curve. And then in the case where a curve is a smooth elliptic curve, this is actually trivial, but where we have all of our roots are real, the root systems are actually the same. In the case of a curve, we can actually sort of explain this sort of larger algebra, which extends the trivial Kac-Moody part in the case for an elliptic curve.
Why is gamma E2 for?
You can sort of see the D4 Dinkin diagram this way. So it has like Z2 stabilizers at 4 points. So like here, the quotient of an elliptic curve by Z mod 2Z, we have like 4 two-torsion points. Our P1 of the quotient gets turned into the central node of the Dinkin diagram, and we're left with like 4 extra nodes coming out, which is the Dinkin diagram of affine D4. Then we get sort of the Kac-Moody loops is this sort of extra direction, and so it ends up being 2 larger dimension than finite dimensional D4. And it's acted upon by the elliptic Weil group of the corresponding like finite dimensional thing, where I'm going to say a little bit about what an elliptic Weil group is. So elliptic Weil group fits into an exact sequence, where here we have shifts by the root system. Here we have our elliptic Weil group associated to our root system. And then here we have our affine Weil group associated to a root system. So we start with our affine Weil group. This has an action on the root lattice of our right, yeah. Well, maybe just the RZ or something. Yeah, it's literally just the lattice itself. Yeah. So affine Lie algebra like acts on the root lattice of our root system. And then this also acts on itself by translations. And this corresponding extension is like an elliptic Weil group associated to these. And that together with Verdi duality acts on the space of quantizations of these cotangent bundles.
Affine already contains some root lattice reaction?
Yeah, so there's kind of two lattices, and they're in the case of they're exchanged by Fourier transform. Exchanges the like root lattice in the like affine part. So this description that I gave is like a reduced symmetry description. So there's like an outer automorphism of SL2Z that exchanges this translation by a lattice and the translation by a lattice that's already in the affine Weil group.
It's like double affine Weil.
Yeah. So elliptic is like, we have.
What goes wrong for k equals 5?
I don't know how to construct. Yeah, that's just not an automorphism of an elliptic curve.
It's like asking to have a quasi-crystal in the plane. Like a static of a plane with a vertex.
Pentagon.
All of these quotients take the elliptic curve for P1, right?
Except for k is equal to 1, where it's just the elliptic curve itself. Yeah, it's all P1. Yeah, quotients of curves always have like a lower genus than the curve. And so they're all just sort of stacky P1s.
But still, we had some, there was a meaningful definition of GL0 double head last time. But with one head, this is somehow still, this is.
That one's actually stupid. Like, GL0 double hat is actually quite interesting. The actual just GL0 hat is really a kind of a boring object to study, I think. Okay, so
Sorry, so somewhere at the beginning we started with instanton on T star E, right? And then now we'll start instanton on T star E mod this group action, right?
right, yeah.
Sorry.
Or it's probably better to think of them as instantons on like a derived equivalent surface where we've replaced the like orbifold structure with the resolution on the surface. But like you can also exactly think of them as these orbifolds, yeah.
But
Sure.
if you were to study instantons and string theory on T star E, the first thing you do is you T value and get some. Probably mentioned two things. In fact, there wouldn't be instantons at all.
Right. So the T duality exactly is this SL2Z automorphism that exchanges this root lattice with the affine here.
Oh, I see.
So you have an SL2Z of T duality given by derived autoequivalence as the elliptic curve, and the Fourier transform, like the one that's usually just called T duality, exchanges the afferent lattice here with the afferent lattice there. And so we capture, yeah, not just instantons, but also their T dual images, and yeah, all of the SL2Z translates those. Great, and so the root hyperplane is exactly, yeah, so there's T duality exchanges this commutative root hyperplane with its SL2Z conjugates. And in the case of, yeah, so let's do Cartan tape A-1, where curly C is actually equal to the elliptic curve. We just get something 2 dimensions, and here we have delta perp, and then its SL2Z conjugates are well, we have T dual of Fourier transform that exchanges this and all of its conjugates, all of our root hyperplanes are delta RD perp, where R and D are integers, and this is exactly the root lattice of this GT star E that I talked about on Wednesday, or the root hyperplanes associated to pairs of integers. So there's no, the same as the Heisenberg algebra has roots at integers. You're going to have like slope Heisenberg algebras, yeah, whose roots, yeah, you only get them Hope prime at hyperplanes the same way that, like, you know, there's only one like root hyperplane for the Heisenberg Lie algebra, despite the fact that you have roots labeled by integers. Great, and then okay, so how do we construct construction of correspondences which act by.
Sam, I apologize. In this story of Bob, is SL2 always present, or SL2? So there's this kind of the S and SL2, that's the Verdier duality,
So Verdier duality is reflection across the commutative hyperplane, and then SL2, which is this 90-degree rotation, is the Fourier transform, which has these equivariant structures. So the Verdier duality is like not really part of this because people usually don't take you know, the like reflections along like isotropic roots, which corresponds to like T goes to T inverse in the affine Lie algebra.
What I was asking is that this is SL2 is some kind of extra structure, or is it arises from some generator that already written before?
It's generated by Verdier duality. So if you take 2 reflections along isotropic root hyperplanes,
I thought that GL0 did somehow. Is there some reflection in GL0?
yeah, precisely T goes to T inverse in GL0. It's a stupid reflection that at the level of like the actual.
SL2 generated by 2 reflections?
Precisely. It's more like GL2. So generated by the reflections here. So we reflect across that, and then we reflect across you know, all of the perpendiculars to these isotropic roots, and it generates, yeah, like GL2 rather than SL2. The GL2 generator has come from these Verdier duality that aren't part of the elliptic well group, which is why we get something which is, yeah, so GL0 hat, despite being completely trivial, still has a a z mod 2z like automorphism that is just the duality of the curve sending t to t inverse, and that's precisely corresponds to Verdi duality.
What's T? Big T?
Small t, so these are all like affine, so the Kac-Moody is like loops into an affine Lie algebra. The affine Lie algebra is like loops into a finite dimensional semi-simple Lie algebra. This has a duality that's usually not considered, that sends the curve to its, that inverts the parameter of the curve. And that's still an automorphism of affine GL0. In the same way that it's an automorphism, all of those, that's going to correspond in this construction to Verdi duality. T inverse, yeah, to T inverse. And so despite the fact that, yeah, GL0 is trivial in this plane, we have, you know, all of these like affine root hyperplanes associated to GL0, and Verdi duality of these generates GL2z, which contains SL2z. That SL2z is exactly this T duality exchanging points with like sheaves of like various ranks and degrees. Okay, how much time do...
Well, come to the. We need to hear the end of it.
Yeah. Actually, I need a 1 minute break just to change the
Okay,
laptop.
we can all use the 1 minute.
Okay, yeah.